Alright, moving on with our review, part E, evaluating, am I making up words? Evaluating limits based on graphs. I think there's supposed to be an A in here somewhere. Maybe right here. Evaluating. There, that's better. Evaluating limits based on graphs. To me, this is the easiest part of this chapter, and this was the very first thing we did. And you're like, this is great, I want to test on this right now. I give you this big crazy graph with all kinds of things happening, bunch of holes, jumps, asymptotes, bunch of neat things, and I ask you to answer these questions. So let's look at number A. The limit as x approaches -3, and this is from the right side. That little plus sign means we're coming from the right side. So I go to -3, and I like to visualize a dotted line. Hang on just a second, I want to fix my lines here. Alright, so if we're approaching -3, what I do is I visualize a dotted line, like a vertical asymptote type thing, at -3. So here I am looking at -3, and I want to know what happens as I'm approaching. I want to make that a little bit thicker. I want to know what happens as I approach -3 from the left side. Or is it the right side? From the right side. So as I get close to -3 from the right side is coming down. This is the right side, and my right side is going down here. So as I follow my graph, as I get close to -3 from the right, we're coming in at a y-coordinate of -1. So from the right side of -3 just to the right, I can see that this function is coming in at -1. As x approaches 0, if I don't specify a side, that means we're looking at both sides of 0. And as x is approaching 0 from both sides of 0, left side and right side, both sides do go to the same place. Now I didn't put a big bold point there, but they do both go to that same place right there, and left and right sides are both going to a y-coordinate of 1. So the answer to B is 1. Number C, x approaches -3 from the left. So now we're going back to -3, -1, -2, -3. Only this time we're looking at the left side. So the left side of -3 is going up towards this open circle, and that open circle is at a y-coordinate of 3. And then part D is what's happening as x is approaching 3. This means we have to look at both sides of 3. Let's see. Oh, that's 3, not -3. I need to move over to 3. So let's go over to 1, 2, 3. So 1, 2, 3. I'm going to look at both sides of 3 here. And as I approach 3 from both sides, the left side goes towards that open circle. The right side is going towards that open circle. And as I'm going towards that open circle, both sides do go to that same place. Now, there is a redefined point up here. That big point has nothing to do with the limit. Whatever's happening on this dotted line does not affect the limit. What I care is that the left side and the right side are both going towards this open circle, and that open circle is at a y-coordinate of 1. So that's the value of the limit. Now for part E, f of 3, this is wanting to know what's happening exactly at 3. We're not looking at the left, we're not looking at the right, we're looking specifically at x equals 3, and that's where this big point comes into play right here. So for part E, we are now looking at this big point, and that point is at a y-coordinate of 4. That is the ordered pair 3, 4, and so f of 3 does equal 4. Number F here, f of -3. F of -3, so we're going over to -3, and if it's f of, that means you want to know what's happening exactly when x equals -3. And when x equals -3, I have a bold point right here, and that's at a y-coordinate of -1. G, x approaches -1 from the right, so let's go to -1. -1 from the right. Now this is interesting because -1 is a vertical asymptote. Now as I come from the right side, this is the right side over here. From the right side, my function is going up forever. So we will say this thing, as x approaches -1 from the right, going towards infinity, because the function's going up. As x approaches -1, then I have to look at both sides, and both sides are going in opposite directions. My right side is going up. We've already looked at that. My left side is going down. They are not going in the same direction, so this limit does not exist. Number I, as x approaches negative infinity. Well, that means what does this function look like it's doing as we go forever to the left? So as I keep going further and further left, and what I tried to do in this graph is show that this thing is starting to level out. It comes down, but then it levels off, and it looks like this thing is going to level off at a y value of -2. It looks a lot like I have a horizontal asymptote right here as I go towards negative infinity. And it looks like my function's kind of leveling off as I keep going. So I would say this answer is -2 because that's kind of where we're leveling off. A similar question that I did not ask, a similar question, we'll call this just a random question, but the limit as x approaches positive infinity of this function. As I go towards positive infinity, well then I'm looking to the right and it looks like we're leveling off up here, and positive infinity looks like there may be a horizontal asymptote on the x-axis, which is the line y equals 0. So I would say as x approaches positive infinity, the limit is 0. Name all x coordinates for which the function is not continuous. To me, this is an easy question because basically all you have to do is imagine yourself drawing this graph, and every time you have to pick up your pencil to draw the graph, that's a discontinuity. So as I follow my graph from the left, as I come up here, okay, at x equals -3, I have to jump from here to here. So x equals -3 is a jump, discontinuity. And then I keep following, keep going, and I'm continuous. I go, and then when I get to x equals -1, I have what's called an infinite discontinuity. That's infinite, or you could simply call that, whoa, misspelled infinite. Or you could call that a vertical asymptote. At +1, we have another jump because I have to pick up my pencil there. And at +3, that's what I call a hole because both sides are going towards that spot. That's what I call a hole, or you could call it removable. And there you go.